Good afternoon. Today I'm presenting NAVIS AI, which is an assistive vision-based navigation system for low vision users. My name is Biniam, and together with my team, we developed a wearable AI system which is designed to improve independence and safety for visually impaired individuals. And this project was conducted under the supervision of our Dr. Mural. So to begin with the challenge, we have like over 2.2 billion people globally live with vision impairment. So for them, everyday navigation, even in an environment which is familiar for them, it can be unsafe and stressful. And we do have traditional solution which can include the white canes or like guide dogs, but these solutions they only takes only the ground level obstacles and they provide no environmental understanding and they cannot also support real time decision making. So this creates a gap which is a critical and users also needs these gaps like the user needs continuous and also real time navigation systems in which these traditional solutions lacks. When you see the existing solution for this problem, we do have smartphone-based systems like Seeing AI or the Lookout. They provide useful features, but they requires the user to hold and aim the device, which limits the mobility. And we do also have the wearable system like the Orcam, and they improve the usability, but they're costly and they're limited in transparency. But most importantly, what with this solution or this technology, these systems they are fragmented, which means they focus on individual tasks like just object detection or just text reading. But navigation is not only limited to this one, but it also means just integration of perception, reasoning, and also interactions. So this gap motivated for us to build this system, which we call it the NAVIS AI. So our objective was to design a system that provides real-time obstacle detection and navigation guidance, which integrates multiple AI capabilities into one platform and also operates in a hand-free wearable form. In short, we just need to build a system that doesn't just detect but also guides the user. And to achieve this, we developed NAVIS AI, which is a wearable system which combines an object detection, depth estimation, and also conversational AI. So the user can also have conversation with this system. And the system continuously analyzes the environment and provides real-time audio guidance. For instance, it can say there's some obstacle ahead, so just move to the right. And it can also say there's one person approaching from the left, so maybe go to the right side. So which means this is transforming the visual input that we have into actionable into something that has actionable navigation decisions, right? So when you come to the methodology, we can see how the system was built and evaluated, right? So regarding the data set, we used, or the data set consists of nearly 3,800 images in which we collected from indoor environments, which can include the corridors, classrooms, and offices. And we applied the stratified split, which means we use 2800 of it for training, 621 of it for validation, and 312 for testing. So this ensures that the test set remains completely unseen and allowing accurate evaluation of the generalization. And regarding the AI model that we use the YOLO just for optimized for the edge devices and the MIDAS for depth estimation, which enables distance prediction using the single RGB camera that we have. And the model used, which was just fine-tuned for 100 epochs, which using the transfer learning from pre-trained weights. And we evaluated the performance using the precision, recall, and also F1 score. And we do also have the confusion metrics. And this ensures both the accuracy and reliability for real-world navigation. When you see the architecture of this system, it follows a four-layer architecture, which means in the hardware, we do have the devices that we can use the camera, the microphone, and the wearable component. In the edge AI, we have the real-time object detection and the depth estimation. So this component is responsible. So whenever the user it just scans the distance or the distance, if let's say the thing that to be scanned was the obstacles and it's responsible for estimating the distance from the user to that obstacles. And we do have also the cloud layers, which is used for basically for reasoning using the visual language models that we have. And we do have also the voice interface. This one is basically used for speech to text and also from text to speech, because in the previous slides we said whenever there's some kind of obstacles, this device will tell for this user there's some obstacle, let's say to the right on the left side, so move to the right side. So we do have speech to text and text to speech in this layer. So this design overall separates the low latency safety tasks from the high level contextual reasoning. So it ensures both the speed and intelligence. When you see the pipeline of a system, so this system uses a parallel dual system stream pipeline, which means we have the fast path and the slow path, which means this fast path is a safety first, right? Which means it handles real-time safety critical tasks like obstacle detection and navigation warnings. And the slow path, it handles on-demand intelligence, which can be like scene understanding and conversational interactions. So this the decoupling between the fast path and the slow path is critical because it allows immediate response for safety while still providing the deeper contextual assistance. So this is a key architectural innovation in our system. When you see the implementation of this system, or when you see how it operates, first it captures the visual input and detects an objects and obstacles, and it estimates the distance between the user and these obstacles, and it prioritizes the relevant information. So instead of just overwhelming the user, it generates a concise and meaningful audio feedback. For instance, there's door on the left, which might be somehow the possible exit or possible destination for you, something like that. So this reduces the cognitive load and improves usability. When you see it further here, this system detects multiple objects, right? We don't have any one object in a given space. So we do have multiple objects. So after that, it understands the spatial relationships between them and it converts them into navigation guidance. So using this specific scenario, you can see like it detects an object, checks the relationship, and detects and guides this specific user on how to approach in relative to these obstacles. So when you come to the innovation and novelty, the first thing that we have is the architectural novelty, which means, as I said before, in the pipeline, we do have a dual fast or slow pipeline, right? Which separates latency critical and reasoning tasks. And when you see the design novelty, the bone conduction audio just preserves the hearing, then stigmatizing glasses from the factors, right? And we do have also the adaptive confidence or intelligence, which is just the dynamic confidence threshold based on the risky environment that we have. So, in short, this system is just not a model. It is like a complete assistive for the user within the system design that we have. And when you see the impact and significance of this, as we mentioned in the early beginning, we said like 2.2 billion people are affected globally with this, and more than 16 millions are expected to be blind by 2050, right? And these traditional method that we discussed before, the guide dogs, they cost more than $50,000. But what does Navis AI offer? So this system, it offers scalable and affordable alternative, right? And even when you see in performance wise, we do have high precision or strong precision in recall. So just beyond the technology that we have, it supports independence, employment, and also social inclusions. And this also aligns with the UA vision for AI driven accessibility. When you see the current limitation and the future roadmap for this system, so as we said before in our data set, it was limited to the indoor environment. And also there is limited representation for certain classes like wheelchairs. And there's also cloud dependency introducing some latency. And there's no large scale user study state. So in the future, the future works, it can include expanding from this indoor environment to outdoor and dynamic environment where the change is high. And also using on-device AI just to remove the cloud dependency and user studies with visually impaired participants so that we can know how well this Navis AI performs. And we do have also integration with GPS for full navigation support. So in conclusion, this Navis AI demonstrates the real-time navigation systems and unified multimodal AI platform. And we do have also the strong performance, as I said before, even an F1 score of 0.85 with a high precision. And it is also user-centered design, this wearable design. So what we can conclude from this is accessibility is moving from isolated tools to integrated, intelligent, and wearable system. And that is all what Navis AI is doing, right? It represented a validated step in that direction. So thank you for your time and attention. And we will be happy to answer the questions related to this presentation and this paper.